And Darwin's going to be my enforcer on this for lab cleanup. If you take the probes off the oscilloscopes, put them back on. If you take a probe off for any reason, put it back on, because if you don't, it makes support extremely annoying. The wire box, the used wire box, should have nothing put into it except used wire. And you'd think that'd be pretty obvious, but I find clip leads, USB cables, and anything that looks vaguely wire-like in there, including integrated circuits. Nothing goes in the wire box but used wire. Single strand, number 22, solid wire only. Power supplies get put away with the board. Speaker box has only speakers in it. No audio cables, no used wire, nothing but speakers. And when you put them back, you put the speakers together, you wrap the cables around them, and then you put them gently in. What's been happening is people have been digging in the speaker box for audio cables. So you go dig, 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 and they get all scrambled up, and then I have to unscramble them. And so what's going to happen is, from now on, if you go into the lab, if I come into the lab and the speakers are not neat, then whoever happens to be in the lab is going to fix it. This is what's called peer pressure. And lastly, audio cables go in a box. You should have all gotten an email this morning describing this, but you probably haven't read it yet. The cabinet where the DE2 boards are kept has a plastic box in the lower right corner. That's where all the audio cables go. Do not put them in the speaker box, because you can't tell the speaker cables from the audio cables, and therefore they get randomly scrambled. Things that look alike have to be kept separate so that you can discriminate them. So audio cables go in the audio cable box, speakers go in the speaker box. Only number 22 solid core wire goes in the wire box. And scope probes always get reattached. Always. I'll yell at you if you don't do that, because it makes support of a lab impossible when things keep changing. Lock the cabinet. It was open this morning when I got here at 7:30. We're not the only class that uses that lab. It needs some moderate amount of security. I will lock you all out of the lab at night, unless you conform. I can do that. I can make it so you can only work during office hours. Don't make me do that. All right, enough of the harsh rhetoric. Any last minute questions about Lab 2? One thing I must say is these are not equivalent in the stack language. This is an assembler command. This is an unknown symbol in the compiler. Anything else? Any other questions? Okay, so let's continue on Lab 3 then. I think I got to the point where I was in the MATLAB code where I was just getting ready to update to do the main iterative update. That's where I was. And we had a vector t at time, so we're just going to say for all values of t equal to time, then we are going to, oh yes, we need to have a t index since values of time are not integers, we need a t-index variable. And we're going to say that the audio output, which is indexed by t-index, is going to be given by the value at the center of the drum. And of course, in MATLAB notation, this means the drum has to have an even number of nodes. So we're just going to take the output near the center. The update then, in cleverly vectorized form, is that we're going to update all of the nodes from 2 to n minus 1 and from 2 to n minus 1, because we don't need to update the first node, because that's fixed. If it's a drum head, that's fixed at u equals 0. And we don't need to update the last node because that's fixed at u equals 0. So we're only going to update, this notation means, if we have n by n array, that we're going to only update the nodes interior to 1 and n. 1 and n. Right? 1 plus 1 over eta times big brackets. Well, we better not use big brackets here because MATLAB doesn't know from big brackets. Rho. This is the speed of sound, so this is the attenuation, and this is the speed of sound. And U1 is the output from the last step. And we're going to use the value 3 to n. 3 to n means while we're updating 2 to n minus 1, U1 goes from 3 to n, so that's the right-hand neighbor. Right, these are all the vector values to the left, to the right of these points. 2 to n minus 1 plus U1 1 to n minus 2, 2 to n minus 1. So that's the left neighbor, whose index is always 1 less in x than the value we are calculating. So in terms of MATLAB efficiency, this is nice because it updates the whole square array in one statement. So there's no nested loop here. You have a time loop. You have to have the iterative time loop, but you don't have to have an iterative space loop in MATLAB because you can vectorize the whole update. Plus U1 2 to n minus 1, 1 to n minus 2. That's the upper neighbor. And then let's see if I got them all here. No, I need plus U1 2 to n minus 1, 3 to n, minus 4 U1 2 to n minus 1, 2 to n minus 1. I like these equations that go all the way across the board. That's cool. Hard to track, though. It's really bad for video. I'm sorry. 2 times U1 2 n minus 1 2 n minus 1 minus 1 minus eta times u2, that's a sample from 2 steps ago, from space index 2 to n minus 1, 2 to n minus 1. Need another bracket and another bracket. Then we have to enforce the boundary conditions. So we have to say that u1 colon, that means all of the rows that have index 1 and then all of the values in that column or in that row are equal to u2 colon. That enforces that actually enforces a equality boundary condition. We're not going to bother to do that. We're just going to set the boundaries equal to 0 for this one, for this example. We say u2 equals u1, u1 equals u, t index equals t index plus 1. And if t equals 0, u1 equals u1 plus u hit, where u hit was the input distribution. And if and end the loop. So the floating point version of this if you run this thing for a reasonable sized drum, let's say 16 by 16, and you plot the, I guess I should say something about drums first. So, let's say first, are there any questions about this? This is a vectorized update of an entire array in one line of code, which is very efficient in MATLAB. It's a little hard to parse, but it runs pretty fast. Still doesn't run real time, even on my desk machine with a big processor and lots of memory. It runs at about half real time. So, of course, what you're going to do is use the MATLAB as a way of testing different rows and etas and getting some feel for how many bits you have to carry in the calculation. And I did this. I did a small exercise to ask if we quantized eta, row, and u, the calculation of eta, row, and u. If we quantized these to 7 bits, 8 bits, actually 7 bits, 10 bits, 13 bits, or 17 bits, how did the sound work coming out? And you can do that fairly easily by truncating the calculation. And what I found is that with and alpha has to be truncated also. If we kept 7 bits, which corresponds to about 2 places of accuracy, about 1 part in 100, and we press the button, or you excite this equation with unity amplitude, and nothing comes out. The resolution is too low; it doesn't work. If we have 10 bits of accuracy, that's about 3 places. It's about 1 part in 1,000. Then we get, so this is no sound. If we truncate to 10 bits, then we get a very short duration and a spectral shift of 10%. Now what do I mean by that? I mean that we have an expected distribution of frequency versus amplitude for a drum where the fundamental frequency is 1. 1 corresponds to where the drum is oscillating in phase. So that's the frequency at which it oscillates in phase. The next normal mode for a square drum is at 1.58 times the fundamental. A string, a one-dimensional wave equation, always gives you integer harmonics. But a square drum, it turns out, gives you non-integer harmonics. You also have a harmonic at 2 and at 2.1 and at 2.6 and a whole bunch of other weird places. If you have high precision arithmetic, if you use full 24-bit IEEE arithmetic, then the drum simulator produces peaks that look like this, and they match up to about the 6th harmonic, 5th harmonic or 6th harmonic. After that, they're off a little bit for various reasons. However, with only 10-bit accuracy, all these peaks are off by 10%. That's kind of acoustically unacceptable. With 4-place accuracy, 13 bits corresponds to 1 part in 10,000 or so. There was a little bit of shortening, and the spectral shift was 2%. That's not so bad. And with 17-place accuracy, so that would be 17-bit accuracy, that would be 5 decimal digits, 1 part in 100,000. Then there was no detectable change. In other words, 18-bit arithmetic is probably good enough for this application. So, using the MATLAB code, you can fiddle with the required accuracy, you can fiddle with the parameters, but you're going to want to do at least 17-bit arithmetic. 8-bit arithmetic isn't going to hack it. 24-bit full precision IEEE is overkill. You might use 18-bit floating point, but you probably don't even have to do that. You can probably just use 18-bit fixed point. You might want to go a little bit higher because some of the constants are rather small. If you have if you have eta fairly small, you have a constant in there which is you have one constant which is 1 plus eta delta t over 2 to the minus 1. So a Taylor expansion, as I said last time, means that this is very close to 1 minus eta over delta t over 2. As long as eta delta t is much less than 1. And so you're going to have to represent a number fairly close to 1. That might be a number like 0.9995. And you're going to have to keep enough bits so that you can resolve that number from unity. This is going to have enough significant bits to be different than 1. Now you could choose this number 1 minus eta delta t over 2 gets multiplied by everything else in the whole formula. What if you chose that so that eta delta t over 2 happened to be a power of 2? What if you chose it to be, say, 2 to the minus 12? You know the usual, the rule of thumb is you take the exponent, divide it by 3, and you have the number of decimal digits, right? You know that from somewhere. So 2 to the minus 12 is about 10 to the minus 4. All right. So you have about 2 to the minus 12. The number is actually 3.2, but who's counting? So that's about 10 to the minus 4. So you could represent 1 minus eta as multiplying by 1, doing a shift by 12 bits and adding, subtracting. Instead of doing the multiply, you replace it with 1 subtraction. If you choose eta delta t to be a power of 2. Since you don't have many multipliers to work with on this chip, optimizing to get rid of multiplies is a good thing. Also, adds and subtracts are faster. So you're probably going to want to choose this to be a power of 2. Probably going to want to be some power of 2. At one point in the equation, you need to form 1 minus eta delta t over 2 over 1 plus eta delta t over 2. And clearly, any ratio, complicated ratio like this, you're going to want to pre-calculate and store. You're not going to want to do this on the fly for every node update. So what's that approximately equal to? Exactly. So we can break this into a couple of steps and say that 1 over 1 plus eta delta t is 1 minus eta delta t. So we have 1 minus eta delta t over 2 squared. And when we expand that, we're going to get 1 minus 2 times eta delta t over 2 plus eta squared delta t squared over 4. But if eta is small, this must be very small. And so we're left with just this. So, and that's nice because, again, we're left with only 1. The multiply becomes a subtract because you're multiplying by 1, and then you're subtracting off a shifted value of the product. If you do if you don't keep enough significant digits, if you start getting excessive rounding errors because of multiplying by these small numbers, what you're going to find is the system will become unstable. And it will start to oscillate at a rather high frequency, which is determined by something like the aliasing frequency on the grid. So you're going to, and the symptom will be, you press the button for a drum strike, and instead of going boom, it goes whee! All right? Because it'll very quickly saturate to some high frequency square wave and blast you and all of your neighbors. So turn the speakers down when you're testing. And that's a sure sign that you're going to have to carry more significant digits, or you're going to have to increase the damping so that you have a damping value which is significantly less than 1. Or you have an eta, 1 minus eta delta t, which is significantly less than 1. You're going to be able to tune, some of you get into tuning, you can tune the drum by changing n, the size of the grid, or by changing rho, the speed of sound on the grid. Making the grid bigger, making the drum bigger with a constant speed of sound suggests this should go to a lower frequency because you have a bigger mass moving. Going to a lower speed of sound takes you to a lower frequency. So you can tune in two different ways. However, in these normalized coordinates, rho always has to be in the range of strictly less than 0.5 for stability. So, how are you going to organize this thing? How many people are going to go fine-grained? Fine-grained. How many people are going to go coarse-grained? Now, you have to have an opinion now. No choice. You have to have an opinion. You have 1 minute to think about it, and then give me your opinion. Okay, who's got an opinion now? Fine grain? So I see a couple of hands for fine grain. I see one shaky hand back there doing something equivocal. Coarse grain? Superscalar monster processors? NIOS 2, by the way, is a predefined MIPS processor. There's an intellectual property that comes with the chip, with the Quartus 2 compiler. It's called SOPC Builder. You can build a CPU with 10 mouse clicks. And then getting the compiler to work will take you the rest of the week. Building a CPU is easy. Learning to use the compiler I found difficult, although you might not. I find an Eclipse interface just bewildering. And some of you, if you've used Eclipse a lot, will just be able to use it immediately. But I don't like it very much. However, it is available. It has floating point arithmetic units predefined. They run at full CPU speed. You might want to look into it. You could use the stack processors. You could use multiple stack processors, each one updating 10 nodes. What are your thoughts? You said you're thinking about going fine grain, Joe. So it fits into your brain well, and it has a certain simple aspect to it because because there's no sort of high-level control structure, right? Everything's low-level control. You have very regular nearest neighbor communication on every cycle, or every few cycles. And that does have a certain appeal to it. Other opinions? Luke, you had an opinion back there? So it wouldn't be a full computer. It wouldn't be a Turing complete computer. It would be but it would be more than a state machine. It'd be something with a series. It's doing fetch executes, but the fetch executes are very specialized, probably. Something of that sort. Yeah. Okay. What else? Any other thoughts about this? If you're going to do a very fine-grained version of this, you're going to find that you're going to be building a lot of extremely repetitive Verilog. You're going to define a module. For instance, you could define a module which is going to be a node, and then you're going to have to make 100 copies of it, each one with slightly different parameters corresponding to which nodes it connects to, which is going to make a very hard to update and maintain chunk of code. How would you approach that? Pardon me? Generate command. Yeah, and I'll talk a little bit more about that. I should have looked at that more this morning, but I haven't. But I'll try and do something with that right now. Some of you who like Perl could write a Perl program that generates Verilog. You could write a MATLAB program that generates Verilog, which is what I would do, because MATLAB is what I know best. One guy 2 years ago wrote a very complete Python generator, a Python Verilog generator. But if you look up, who's got a laptop open? Besides, no, not you. So we got a laptop open? Nobody's got a laptop open? Ah, there's a laptop, or a tablet. Look up Verilog Python generator. I believe there's a website that has such a piece of code already written. You find something? My HDL, love it, and it's some sort of parameterized generator of some sort. Well, as of Verilog 2001, there's a generate command which is peculiar because it is it's kind of a it uses constructs that only exist at compile time. So you have you can define a genvar, a generate variable that only exists while you're elaborating the logic, does not exist on the FPGA or at execute time. And you can use a genvar as a parameter to step through objects that you want to repeat. So let me see if I can come up with an example here that makes sense. So, oh, an 8-bit shift register. Let's see if I can do this. We have a genvar n. Then we're going to start a generate block. Then we're going to say for n equals 0, n less than or equal to 7, n equals n plus 1. Begin. We have to give it a name, which is going to be flops. We're going to generate a bunch of flip-flops. And if we have a primitive called D flip-flop, D-flop, so that would be a D-type flip-flop, U, then we can say clock gets clock dot in is equal to path n dot out equals path n plus 1 and assuming that some path has been set up someplace outside this gen block, one path has been set up, has to be, let's see, path 0 has to be set up, then this will wire a set of flip-flops as a shift register. So you can generate a complicated, and you could have nested for loops, so you could do a two-dimensional array of connections using the generate block and put something together that is much more compact, easier to modify. And I'll try and come up with a more complete example by Monday. But look at generate statements. I think if you're going to do fine-grained stuff, you're going to need that for this lab, unless you like doing a lot of copy and paste and editing. So are you thinking floating point or fixed point? Fixed point? Fixed point? And I guess I would strongly encourage you then to make sure that all of your compute models are parameterized for the register width. So rather than hard coding 18 bits or 20 bits, set up the width of the buses so that they scale well. So if you have some variable name, give it a value of n down to 0 so that you can change n in one parameter one place in the program to rescale everything to a bigger size. And if you suddenly find in the middle of developing this that you have to go to 20 bits rather than 18 bits, it won't matter. Unless you include explicit multiplies. If you include explicit multiplies, you're going to have to worry a lot more about the width of the word and how many bits of fraction you're carrying, because the interpretation of the multiply changes. But if you can avoid multiplies altogether and do everything with shifts and adds, then you can change the width of your computation extremely easily. Treat everything as an integer. Do everything as shifts and adds, and never do an explicit multiply. Unless you decide to go floating point, in which case you're going to have to do explicit multiplies. Floating point, by the way, does not help you with the problem of the number that is near 1. All right, you can have, if the number is very nearly 1 and you're trying to maintain a significant difference than 1, you still have to have just as many bits in the floating point as you do in fixed point. So you don't get to narrow the width of the calculation by going to floating point. You still have to have 18 or 20 bits. But it does simplify the multiplies somewhat. I mean, it simplifies thinking about the multiplies. It doesn't simplify the implementation of the multiplies. So everybody's going to go fixed point? All right, well, let's get back to the lab and get ready for the afternoon, because I'm sure some of you would like to be doing that rather than sitting here.